Thank you for the introduction, and I want to thank the organizer for inviting me to give talk here in this very nice place. So I basically will talk about three things. First is why we need to consider A packets, and secondly, how we define them, and thirdly, I want to give some examples. So what are the representation in these A packets? Okay, so first part, I'm going to take G to be SO or symplectic. Let's say these are split groups defined over a number field. Okay. Now, for people interested in automorphic form, we would like to understand the spectral decomposition of this L2 space. Okay. And it is well known that the spectrum decomposes into a discrete part and a continuous part. So, and by the theory, by Langland's theory of Eisenstein series, it suffices to consider the discrete part. Okay. And in this particular case, we have a theorem of Arthur in 2013, which says that, well, it admits decomposition. First, it's parameterized by the so-called Arthur parameters. And for each of these parameters, we can associate a set of irreducible representations. Okay. And then for these representations, some of them will show up in this spectrum, some of them may not. There's a multiplicity, which can be 0. Okay. And then pi. Okay. So just let me say a few words about the notations in this theorem. So firstly, what are these A parameters, as parameters? So conjecturally, as parameters, it's kind of like a generalization of a Galois representation. But instead of putting the Galois group, we have to put the so-called hypothetical Langlands group, which is not defined yet. And then we need to put an SL2C and map it to the dual group, G hat. Okay. So that's the conjecture. But since we don't know the Langlands group here, you can put the Galois group. That's just a special case. In general, we don't know what this group is. So instead, we can think this G hat will embed to certain general linear groups by the standard representation. So in this case, G hat will either be symplectic or orthogonal. Okay. So if you compose with these standard representations, instead you can think psi gives you a parameters for GON, which means that, well, we can interpret these in terms of automorphic representations of GON. So to be precise, in this theorem, these parameters are actually represented by the automorphic representations of GON. So you cannot think them just as these parameters because they are not well defined. Okay, so that's for these parameters. And then we have these packets. Now, in yesterday's talk, you have heard these A packets. The reason for introducing these A packets in the classical terminology is that you have these automorphic forms, and they can have the same Heck eigenvalues. Okay, and you're putting these representation in the same packets. So these are the automorphic representation with the same Hecke eigenvalue. Okay? And it's a global object, but it's part of the theorem that you can decompose this, just like you're decomposing a single irreducible automorphic representations. Okay? And these local components, again, they are subset of the isomorphism classes of irreducible representation for the local group. Okay? And we also know that this is a finite. Okay. And finally, there's this multiplicity, and Arthur also gives an explicit formula describing this multiplicity, and that's so-called the Arthur's multiplicity formula. And here I will not explain. Okay, so this is the Arthur packet. So what is our problem? Our problem here is to describe these local packets. We would like to know what are the representations inside these packets. So, for example, this spectrum all the representation is going to be unitary. So in particular, here we'll only be considering the unitary representation. Moreover, the A packet will actually contain something very special. It's not all unitary representations. So you can think that these are the local components of the automorphic representations. They form a very special class. Okay? And they are kind of classified by these A packets. So the main purpose of this talk is to understand these local ones when at non-Archimedean place. Okay. But first, to be able to understand this one, you need to have a description. And here we kind of think that as a local component of a global object. And certainly it's very difficult to work with these global ones, because that's from the automorphic representations. So we need a local description. Okay, and so let me take F to be the p-adic field. Okay, and locally we can write down this kind of local version of the A parameter very explicitly. So here you have the local Langlands group cross SL2C coming from the global SL2C. Okay, and locally, this one is concretely defined in the p-adic place. It's the so-called the Wade-Delane group, which we write as the Wade group cross SL2C. Okay, so in particular, you see there are two copies of SL2C. One is basically from the local Wade-Delane group, and the other one is global. Okay, and again, we can embed this to GONC by the standard representation. So we can think this parameter as an n-dimensional representations of a Wade group cross two copies of SL2C. Okay, so we can break this up into irreducible components. And let me write these irreducible components as rho tensor nu A tensor nu B. Okay. So here this rho is the irreducible unitary representation of the Wade group. And by the local Langlands correspondence, we know that this corresponding to irreducible unitary supercapital representation of some general linear groups, which I denote by GLD rho. Okay. And for this representation, again, I will denote it by rho. And then for this new A, new B, so these A, B are integers. In general, this new M is the unique m-dimensional algebraic representation of SL2C, or concretely, this is the m-1 symmetric power. Okay. So from the parameter, we get all these concrete data, and from this data, we want to construct a packet. Okay. But first, we like to construct a representation on GON. Okay. So how do we construct these representations? Well, I have all these data. So from this row and also integer A, I can form the so-called Steinberg representation. Okay. Pardon? Why it's a direct sum? Yeah, so you can think this is just like a representation of a finite group, something like that. Yeah, we have, in this parameter, we have some conditions. In particular, we want this to be semi-simple. So there are some semi-simplicity built into the definition of parameters. Okay. Yeah, so it's a semi-simple, the way group. Okay. So we have this Steinberg representation, and then together with this B, we can define the so-called Spay representation. Okay. So that's some representation of general linear groups, and from all this, you can do an induction. Okay. So we get the representation of this GONF. Okay. I want to say a few more words about these representations. So first of all, the Steinberg representation. Okay. It's induced from the following representation. So you have this row, and we can twist by some unramified characters. Okay. And you want these exponents to go from a-1/2 to a negative a-1/2. So it's decreased by 1 each step. And you take the sucker of this induction, which is actually the unique irreducible sub-representation. So that's the Steinberg representation. And to form the Spay representation, what you do is you replace rho by this Steinberg representation, and again, you do twisting by unramified characters, and then you do a parabolic induction. So here, I just want to keep track of all these twists, so these exponents. So first of all, for the Steinberg representations, I have this twisting, or the exponents goes from a-1/2 to negative a-1/2. And now I'm going to keep twist on the Steinberg representation. So here I'm going to put negative b-1/2 and negative b-1/2. And then you keep twist the Steinberg representation, and each time you increase this exponent by 1. Okay, so you kind of get a matrix. So just remember that each row represents the Steinberg representations, and you put all them together, you do an induction, and that will contain a unique sub-representation, and that's the Spay representation. So later on, I'm going to use this matrix to represent a Spay representation. And in particular, we'll also see some kind of shifts of this matrix. So the entries are not exactly in this form, but with a shift. Okay. So now we are ready to describe the A packets for G. Okay. So again, I'll state that as a theorem of Arthur. So it says that for that parameter's size there, it's determined by the representation of GON we constructed. Okay? And this determination is through the character relation. So what this means is that for these representations, we can find their hash stranger character. That's a distribution on the groups. So for this GON representation, in fact, since the parameter coming from this G, so it's going to be a self-dual representation. So you can define a so-called twisted character. And the character relation is an identity relating the twisted character on this GON representation with certain linear combinations of characters in this packet. Okay? And in fact, that linear combination is going to be stable. And moreover, just by the linear independence of characters for these representations, we know that this stable character will actually determine this packet uniquely. Okay? So you can think that, okay, this packet is determined by some representation of GON in this way. But the problem is that we don't know what exactly inside the packet. So what are the representations? So that's the problem. But in order to describe the representation in this packet, we need to first to be able to talk about, like to give kind of names to these representations. So first, we need to be able to parameterize this set. Okay? And the parameterization is given by the Langlands correspondence. Okay? And in this case, the Langlands correspondence is given due to Arthur. So there's going to be a bijection between these set of irreducible representations with pairs where this phi is a Langlands parameter. Okay? And this epsilon is going to be an irreducible representation of some finite group associated with this parameter. Okay? So what is this finite group? So this S phi, so maybe just say a few words about this Langlands parameter. They are very like the A parameter, but you just don't have the second copy of SL2C. Okay, so roughly speaking, they are homomorphisms of this kind, and you modulo the G-hat conjugacy. Okay, and then this S phi is going to be the component group of the centralizer of phi modulo the center of G-hat. Okay. So after that, for every representations, we can actually assign, it's kind of a name for this representation. In particular, I'll just write every representation as pi and writing its corresponding parameters phi epsilon in this way. And then we can try to talk about what's inside the A packet. So in this talk, we'll look at a special case. Okay. And so what is the special case? The special case is if we write down the parameter again in terms of its irreducible components. Okay. So that's a general form of the parameter. But now I'm going to fix the component for the second SL2. which means I fix the dimension B. Okay. So what this means? Well, if you think about a global parameter, again, you can try to decompose as its irreducible component, but globally, you only have this LF, and then you have an SL2C. Okay. So the simplest global parameter will be you just have one irreducible component. So the global parameter is irreducible. Okay. And in that case, so you have this new B fixed, but then you look at the local component, then the first part of the global parameter will decompose into a direct sum, and the second part will remain. So this represents the local component of the simplest kind of global parameters. Okay? And in particular, for that global parameter, because it's irreducible, so all the representations, all the automorphic representation, they are not coming from endoscopic lifting. Okay? So in some sense, we're trying to describe the local components of the kind of simplest kind of automorphic representations. Okay? So to be able to describe the results, I want to make some simplification. The first simplification is I'm going to take all this rho I to be trivial. Okay? And secondly, I want this AI and also B to be odd. Okay? And by these two, so we can just write the parameter in a very simple way. So there's no rho, and just have these AI and B. Okay? And since we are assuming this rho is trivial, you can think that now this problem becomes there's no arithmetics. Okay? And all the information is in way just determined by these integers. So in some sense, it should be a combinatorial problem to determine the representation in the package. And indeed, it's kind of in a combinatorial nature. And the difficulty is to finding out the kind of mechanism or the structures of this combinatorial. Okay? So to describe the combinatorial structure of the A packets, we built from this data AI and B, and we need to do a transformation to capital AI, BI, and zeta I. So this is how they are defined. So this capital AI is AI plus B half minus 1. This BI is the absolute value of AI minus B half. And then this zeta I is the sign of difference between AI and B. And in case this AI is equal to B, you can take this zeta I to be either plus or minus. Okay. And once you do this transformation, then you can just picture your A packets or the A parameters in the real line. So you get capital AI and capital BI with the sign. So that's represent an interval. Okay? And in particular, if you have several irreducible components, there will be several intervals, and the intervals can interact or can intersect with each other, and the intersection somehow reflect the combinatorial structure of this A packet. So we'll see in a moment. So just to consider a simplest case when you just have one irreducible component. Let me assume that this A is bigger than B. Okay? So that's the kind of simplest kind of A parameter. And in this case, we have the theorem of Mögelen, which describes the A packets very explicitly. So first, there's a bijection between these A packets and the data in this form, where this L is an integer and this eta is just a sign. Okay? And moreover, we want this L to be range from 0 to a minus b half. And okay, and there's going to be some sign conditions, which I'm not going to write down. It's corresponding to the fact that we are just considering the quasi-split group. Okay. So from this part, you can actually tell what's the size of this A packet. In particular, so this L is actually depend on the length of this interval. Okay. Now there's a second part that we can actually describe all the representations. So maybe I'll write it here. Okay, so for all the representations, they are indexed by L and eta, and this can be embedded into the following induced representation. So first, I'm writing down the matrix. Okay, and remember that the matrix represents the Spay representation for some general linear groups, and in fact, it's going to be some kind of shifted Spay. Okay, and then we have a representations on a group which is of the same type as G, so it's going to be either special orthogonal or symplectic, so which I denote by G prime. Okay. So this representation here is in fact a discrete series. Okay, and we are writing down its Lagrange parameters, phi prime and epsilon prime. So what are the Lagrange parameters? So for this phi prime, again, just like A parameters, we write that as a representation and we decompose into irreducible component. So it's in this form. So remember that the second SL2C is acting trivially. So C goes from B minus L to B plus L to A minus L. Okay? And again, you can picture this parameter in the real line. So now all these components has the second SL2 to be trivial. So they will just be a point. Okay? There's no intervals. And the point goes from B plus L to A minus L. Okay? Moreover, you can describe this epsilon prime. So that's a character on the centralized of this phi prime. Okay? And in fact, you can view the character as assigning some sign to all these points. So this epsilon prime is going to be assigning this sign eta to this point B plus L. And for general point C, so this sign will be alternating. So here it's going to be a -1 C minus B plus L. Okay. So that's this discrete series representation. Okay. And from this description, you can actually read out the Lagrange parameters. Okay. So what is this Lagrange parameter? So in fact, to get the Lagrange parameter, you have to break up all this matrix. So remember that each row represents a Steinberg representation. So the Lagrange parameter for this representation will factor through a Levy subgroups. Okay, so where you have a product of general linear groups of the size A plus B plus 1. Okay. And then cross the dual group of this G prime. Okay. And this will be embedded into G hat as the Levy subgroup. Okay. And you can describe the morphism into this Levy subgroup. So on the general linear factors, it takes the form like this. So it's going to be some shift by the by this unramified character, and then you tensor with a Steinberg representation. Okay. So that's on the general linear factors, and then on this G prime, you have this phi prime. Okay. And moreover, so in this case, we have this a bijection between the centralizer of S phi with the centralizer of S phi prime. So this is an isomorphism. So there we have this epsilon prime. So this goes to epsilon. So the conclusion is that this representation pi L eta, its Lagrange parameter is just this phi and this epsilon. Okay. So now we can look at the general case. So in general, there are going to be several components. There will be several intervals. But since we're fixing B, so you can see that so there will be some A, which is less than B. I index them so that for all the I less than or equal to M, these AI are less than or equal to B. And also for the other ones, it's bigger than B. Okay? And the impact when you're just drawing these intervals is as follows. So for all those AI less than B, you will get intervals which is centered around B minus 1/2. So they will in this shape. And remember, you will give them a negative sign. And for all those AI bigger than B, you will have intervals like this. And so they will all have the same length. And they carry a plus sign. So the length is B minus 1. Okay? And in particular, the plus intervals will be bigger than the negative intervals. Okay, so that's the special shape of this parameter. And now we can state our theorem. So the first theorem is as follows. So I'm going to introduce another parameter. It's obtained from psi by do the following change. So remember that we are writing down the component as these triples A, B, C, A, B, zeta. And so we want for this psi prime to have the following properties. So in case I is bigger than M, I'm going to keep these triples. And for I is less than or equal to M, I'm going to change this to AI minus BI 0 and plus. Okay. And what this means is I'm going to keep all the positive intervals, and I'm going to push all the negative intervals so that their left endpoints reach 0. So that's the picture. Okay, and so the resulting parameter will have this picture where all intervals will carry a plus sign. Okay, so the result is first there's a relation between these two A packets, and in fact, it's a bijection. So I'm sending pi to pi prime. The second statement is, well, what's the relation? So pi can be embedded into the following induced representation where you have pi prime, and here I'm putting a matrix. So that's again the shifted Spay representation. So this matrix is in this form. Okay. Okay. So that's this theorem. So we're now reducing to the case of psi prime. And to treat psi prime, just note that not only they are all plus, they also have the following properties. So for each AI prime, it's going to be bigger than or equal to AI minus 1 prime. And bi prime is bigger than or equal to bi minus 1 prime. And we are taking all these zeta I prime to be plus. Okay. So it satisfies these properties. And in fact, our second theorem will apply to all the cases with this property. Okay. So the theorem is very like Merkle's theorem. So remember, the first part of Merkle's theorem is establishing a bijection between this with a certain set of parameters, as you can see over there. But here you have more intervals, so instead of have a single L and eta, you will have L denoted by lower bar, and they will be tuples. Okay. So this L and eta lower bar will be R tuples. And with the following conditions. Oh, yes. Thank you. Yeah. For all I less than or equal to m. Yeah. Thank you. And so actually there's an order. A priori you can think that, but in fact the order doesn't matter. You can actually switch out this matrix. The resulting induced representation is not changed. Okay. Okay. So here, these Li again, they are less than equal, bigger than or equal to 0, and less than or equal to Ai minus Bi over 2. Okay, that's the same condition. And now we're adding more conditions. So it will depend on the sign for each consecutive intervals. Okay. So in case they have this condition, then we require that this is bigger than this, and so Bi plus 1 Li. And if they are not equal, then we are asking this Bi plus 1 plus L plus 1 is bigger than Ai minus Li. So the R is basically the number of components or the intervals you see in the picture. So if there are intervals, there will be R components. Okay? And indeed, this condition is always satisfied if all these intervals, they don't intersect each other. And in fact, that's also follow from Well, it's due to Magellan. So she has a theorem which not just deal with one interface, but more than one interface. In the case that they don't intersect each other. But if they intersect, that's the condition you need to put. Okay? So this first part, again, tell you the size of this packet. Now, secondly, we want to describe the representations in this packet. Oh, I forgot to say that, again, there's some sign conditions. Okay, so what's the second part? So now we have these representations. They are parameterized by these L and eta tuples, R tuples. So first, we can embed them just like Magellan's theorem. We have this matrix. For all these components, or all these intervals. Okay. So after you take all this, so all these intervals, you think of them, they get shrinked. So let's say you have a picture like this, where this is AJ plus 1, and this is BJ plus 1. So this is BJ. Okay. So they all get shrinked. So say the A will shrink by this L, and also B will get shrinked. And previously, what we do is we just take all the points in these intervals, okay? And then they will give us a parameters, and that parameter will give us a representation for a group of like smaller rank than G. The problem is if these intervals still intersect with each other, then you cannot just take these points, okay? You cannot say, okay, I take multiplicities for these points. So instead, what you need to do is, intuitively, what you do is you think, okay, this right endpoint should go to the left, and you want this left endpoint to go to the right, okay? And by doing this process, you will producing more matrices. So whenever you have a J, so that it has this intersection, so this will be for sum of the J, and then you will get an actual matrix. Okay. And here I'm putting Tj minus 1 and negative Tj plus 1. So Tj will be this middle point. Okay. So that's the actual matrix. And once you do this process, eventually these two endpoints will cross this middle line and they don't intersect, or either they will come to the middle point. So either you will separate these intervals, or they will just intersect at the endpoint. And then you just collect all the points in the intervals. So they may have multiplicities when they intersect at the endpoint. But again, you just count the multiplicity. So in the end, you will get a parameter. And well, you can also count the signs for these points. So that will give you a characters for the centralized upper parameter. So this will be a representation on G double prime. And indeed, when there's kind of multiplicities, so this will be a temporal representation in general. Okay. And then finally, so even though I write like this, where you have a tempered representations, but all these are not tempered. They are Spay representations, and also shifted. You can actually easily write down the Langlands parameter from this. Just like Morgan theorem, what you do is you break up all these rows, and they give you the Steinberg representations. And in fact, what you can show is that this induced representation is just a submodule of the standard module. Okay, so from that you can also see that this representation is the unique irreducible sub-representations of this induced representations. And to go back to our original parameter, you can put these two theorems together. So in the first theorem, we're producing these matrices. And then in the second theory, we further introducing these matrices. You can put them all together. And so the eventual resulting induced representation will again be a submodule of the standard module for the representation you start with. Okay, so you can again get the Langlands parameter for this pi. Okay, so I'll stop here. Thank you.